In this chapter, we've shown how we can derive transfer functions for models of chemical and biological processes. In all of the examples that we've looked at, the model equations were linear. What about models that produce nonlinear ODEs? We can't use Laplace transforms for nonlinear equations, so in order to derive transfer functions for them, we must first linearize the equations, and then take the Laplace transforms of the linearized version. Models of processes that do not deviate very far from a steady state can be linearized using Taylor series expansions around the steady state, truncated after the first order term. For example, consider a dynamic model for an output variable y, where dy dt is some function of y and other input variables u. The Taylor series expansion of f around the steady state approximates f of y and u as the steady state value of f at the steady state of y and the steady state of u, plus the partial derivative of f with respect to y evaluated at the steady state times the deviation in y from the steady state, plus the partial derivative of f with respect to u evaluated at the steady state multiplied by the deviation in u from the steady state. Of course, the Taylor series expansion has higher second order and third order, etc. terms, which we can truncate, and by truncating after the first order terms, we have a linear equation in the deviation variables y prime and u prime. Furthermore, since f of y and u describes the time derivative of y, then f of y bar and u bar must be 0, because at the steady state, the time derivative of y must be 0. If we substitute this linear approximation for f of y and u into the dynamic equation, and then we also identify the perturbation variables y prime and u prime, then we obtain a linear approximation for our nonlinear model. This is a linear approximation because it's a linear combination of y prime and u prime. Note that these partial derivatives are evaluated at the steady state, so both of these partial derivatives are just constant terms. They are not functions of y or u or any of the independent variables like time. Furthermore, note that linearizing a model using the first-order Taylor series approximation writes the model in the deviation variables automatically. So the deviation variables are the natural variables in which the linearized model is written. This method of linearizing nonlinear equations is very powerful, and we'll use it throughout the semester so that we can take Laplace transforms of nonlinear models and still be able to derive transfer functions for them. What we've learned from Chapter 4 of the Seaborg text is that transfer functions are functions in the Laplace domain that relate output variables to input variables. They're derived from Laplace domain equations of dynamic process models and are usually expressed in terms of what we call deviation variables or perturbation variables that describe how a variable deviates from some steady state value. The transfer functions reveal key information about time domain responses. They contain quantities like the steady state gain and the time constants that can tell us a great deal about how processes behave in the time domain. Transfer functions can be written in several forms, and here we introduced the polynomial form and the gain and time constants form. Transfer functions can be used to describe all kinds of phenomena, from chemical reactions to mass transfer, heat transfer, you name it. But they can be categorized according to their structure, that is, their mathematical structure, from which we can begin to recognize key features of the corresponding time domain behavior. So the emphasis here isn't so much on what the physical process is that's being described, but rather on the mathematical form of the transfer function that arises. And we identified integrator, first order, and second order transfer functions. Transfer functions can also be derived for nonlinear models that can be described using linear Taylor series approximations around a steady state. In the next chapter, we'll use this important categorization of transfer functions as either integrators, first order, or second order transfer functions to see what the transfer functions reveal about the time domain behavior of model outputs in response to various types of model inputs.